Yeah, maybe I can just introduce myself for the people that don't know me. I'm Valentina Premier from URAC Research in Bolzano. And today we are supposed to do an hands-on exercise. So I encourage you to take your laptop and try with me the exercise. So for this purpose, my research topic is snow monitoring. And so I prepared some exercises with openEO since we are trying to move to a cloud platform for reproducing our algorithm. But today I'm showing some very basic examples to let you also to be familiar a little bit both with openEO and also with the snow topic. Um, First, I would ask you maybe to scan the QR code if you want to enter in the GitHub repository, GitLab in reality, but so you can start the exercise with me. So yeah, for Simone, if you also want to do the exercise, we start by scanning the QR code to enter the GitLab repository, uh, since this is supposed to be an hands-on exercise. So everyone entered, yeah. So just as an introduction, this work was supported by two projects. One is the Open Earth Monitor project, and the other one is SnowCop. And this is another Horizon Europe project that aims at producing snow water equivalent maps for all the Andes for 20 years at high resolution, daily high resolution maps. So I also mentioned here my colleagues that are working in this project and helped me for the preparation of this notebook. I put also some useful documentation in case I want to reproduce the exercise later, so you can find some documentation links. Okay, so if everyone entered here, now what we need to do, if you don't have yet, to register to the Copernicus dataspace ecosystem. I don't know if everyone has an account there. Otherwise, we need to create an account now. So very simply, sorry, I need to share it again because I was sharing that specific page. Um, okay, let's do like this. So if I need to change sheet, is not. Oh, I see also the. Okay. So you just go to this link and you create an account. So let me know as when you are done. One person is done. The other one. Okay. So once you are done, you go to analysis here in the home page, and you click to Jupyter Lab. So we are going to reproduce. Of course, you can also clone the notebook and run in normal Jupyter not lab in your local machine, but also to explore the potentiality of the Copernicus data space ecosystem, let's access to the Jupyter Lab in the CDSE. So you go there, you access Jupyter Lab, sorry, and I suggest, so you will be asked to log in, and I suggest to choose the option Medium Server. We are not going to do super expensive computations, but let's try with Medium Server. Yeah, now that we are here, let's open a terminal and let's clone the repository. So I will also do with you. So let's check that everything works. Do you see? Yeah, maybe I can make a little bit bigger. Yeah, now we have cloned the repository, and I've prepared also a Conda environment for this exercise. So let's create my openEO environment in order to speed up um, the installation of all the libraries. Okay. Yeah. So now let's, I know I didn't create, let's create now, let's install the required libraries. Yeah. Can I hide it or? Okay, this will require some minutes, but should be quite fast.
While it's inside, can you show the GitHub thing again?
Yes, the QR code or
Let's see. Let's play this.
so okay, the environment is created. I don't know for you, did it work? Yes. Okay. So now let's register the kernel. So let's copy paste the last command. Okay. So everything should be set up. Let me know if it worked. Okay, so if we are ready, more or less, so let's go to the folder demo LPS. I recycled some material from the Living Planet Symposium, so that's why it's called like this. But I added some new exercise for you today. So let's start with the notebook that is called Snow Mapping. So you can open the notebook here. And let's change the kernel here that now should appear. Yes, my openEO. Yeah, so and let's start the exercise. Yeah, maybe just I want just to mention that snow monitoring is a topic of relevance, especially in our area because I'm coming from the Alps. But not only, I was mentioning that we are now working in the Andes, so that's why I'm showing today some exercises for snow mapping. Um, I don't know if you are already familiar with openEO. For sure, some of you are. I don't know if some people don't know at all what openEO is. But anyway, it's an open source initiative that is aimed also to simplify the access and the process of Earth observation data. And you can access to this interface for different programming languages. In this case, today we are using Python. So let's start by importing some libraries and also some additional functions that I prepared for the today workshop. And let's define first the area of interest. So for this specific example, we are going to the Andes. So you can see here, this is the study area. It's called Azufre Glacier and is located along the border between Chile and Argentina. So let's start to import the shape file with the area of interest to define the bounding box of our study area and our exercise. So we are reading the bounding box from an external shape file that it's sharing in the input folder. But of course, you can also try with your study area if you want to change the study area. So you see here, this is the shape of the basin. This is the glacier, this one. Now what we need to do is to connect and authenticate to the openEO backend. For this first part, we are going to use the Copernicus dataspace ecosystem backend. So let's run this cell and you will be asked to authenticate through this link. So let me know if everyone was able to authenticate and connect. No?
Bit late.
Uh,
Because I had some trouble with the registration.
okay, okay.
Can I ask you something? When I open the Jupyter notebook, should I am not able to clone.
Uh,
So
did you copy paste the?
I use this one.
So you go to the terminal. Yes.
Well, you just follow the other steps. Yes, in the. Yeah. So you just put the third, and once it's finished, you'll refresh the page.
Yeah. These are the commands in for the others. Did it work? Okay. Yeah. So let's wait just a little bit. In the meanwhile, I can tell you a little bit about the purpose of the notebook. So the idea was to see how the snow cover properties are changing over the year because When you are in a complete winter, when it's very cold, the snow is completely dry, and the basin will be full of snow. And so from the optical satellite, what we can detect is the presence or the absence of snow. While when we go to spring and the snow starts melting, what we can detect is another property, and is if the snow is getting wet. And for getting this property, we will change satellite and we will use Sentinel-1. And when it's summer, you remember I showed you here that there is a glacier, so the snow is disappearing, and the ice will appear under the snow. So what is also useful to detect is if the surface is snow covered or ice covered. So let's try to do this with openEO. So for the first part, we are in winter. That, however, in South America is in July. So don't be confused. It's just because we are changing hemisphere. So we are basically loading a collection that is in this case is Sentinel-2 level 2A. And we are setting the dates of interest that are in July, that is winter, as I was saying, and the bounding box that are read from the shapefile. We are also loading the bands that are of interest for our algorithm. In this case, we are doing a simple classification that is the state of the art and the most simple methodology by using the normalized difference snow index. So we are just calculating this index and putting a threshold for detecting the snow. You can also filter when you load a collection through openEO. You see that you can also filter the maximum cloud cover. Oh, what happened? No, no, my laptop. No, it's weird because I continue sharing, but it's restarting. So I don't know why, but missed. I hope that it's not an update. Okay, but weird that it's still. Oh. No, 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 no.
Okay. Now you are.
Okay. So I need to connect again to the Zoom. Sorry, I don't know what happened. I should be entering again in the meeting. Yes, I'm there again. So I will be sharing again the screen. Okay, here we are. Mhm.
Yes.
So let's run again just for being sure. Yeah, so I was mentioning that basically when you load the collection, you can choose among different collections that are available in the backend you are using, and you can start by filtering by some very basic properties, so the area, the time frame, and the bands, the cloud cover, or some other properties. So if you want to by documenting this line, so you are downloading the example here is a specific date. Um, However, this netcdf is also already in the output folder. So since we have time, we can also delete here what is in output and rerun everything. So we are launching really the job and we are doing everything real time. It's up to you. I mean, I would do that since we have time. So, but just to back up the files, the output was already there. So, what I will do is to delete everything in the output folder. Okay, so now if it doesn't work, we are lost. But no, I'm sure that it works. So let's document the download. So there are two ways to launch a job. It's through asynchronous and asynchronous process. In this specific case, synchronous, right? So we are doing directly here. If you do through an asynchronous job, in that case, the job will be also visible in the web editor. That maybe I will show you later how it works. So for now, since this is also a quite fast job and it doesn't require so much time, I suggest you to do in this way. So you see it's very fast. We already have our download.
I did download, but I didn't make it.
No, I mean it's just overwriting, but no. So in this case, I also need because I gave another name. So let's change here. The name is or maybe just not to confuse the dates, because then we are downloading other dates. I rename here the file. So 2024 July 16 to keep trace of the date. And yeah, here we have we can see the false color composite of this Sentinel-2 image. So you can see that it's very already user friendly, and you can see where there is snow and the small spots where the snow is missing. Yeah, so to classify the snow, as I was saying, we can use the normalized difference snow index. That is simple, this normalized difference between the green and the SWIR bands. So let's apply this for some very basic openEO processes. So again, let's document the download line. And you can see that, yeah, also the syntax is very user-friendly, and you just compute the difference and the ratio. So I'm plotting here also the the process graph of openEO. So basically, you can see what you are doing through the functions that you are, the process that you are calling. So first a load collection, then we perform this operation that is a reduced dimension in this case. So basically you see in another way what you are doing. And this process graph you can also create directly from the CDSE web editor. If you don't like coding and writing your notebook, it's another way to do it. So now let's see if it worked. So applying this threshold worked, and we were able to classify the image. And yeah, you can see that I'm applying here already a color scale. You can see that despite the algorithm is very simple, you can already classify quite well the snow-free spot areas and the big snow area. Okay, so everything is clear. What we are doing also in the SnowCop project now is to move also to more complex algorithms. So since the classification, this is a quite good scene without specific problems, but when you have areas that are in dark shadows, it might fail to classify with these standard algorithms. So we have developed in Europe our own algorithm that is based on machine learning to classify the maps, and we are trying to transfer it to openEO, but we are facing some challenges, especially linked to the fact that we would like to train the machine learning model for each specific scene and online in openEO, and not use a predefined model. And so this is a little bit challenging, so it's still under discussion. So let's move to the second exercise, and also, yes? Yes.
So you mentioned that this index is based, or maybe read it, is based on the fact that the snow is reflecting a lot of the shortwave radiation. So basically, more or less, we could already see in the map, in the first one, where are the snow-free spots. However, there is I'm curious to know if this, there is this point, let's say, in the middle.
You mean this one? This?
No,
No.
the one on the top.
Here.
This one, yes. This one,
yeah.
Not.
Yeah, it's not recognized in the classification.
It's not recognized. It's not actually
No, probably now we would also need maybe to zoom better the image and stretch it in QGIS to visualize it better. But my suspect is that it's since it's on the top of the mountain, probably the snow is going away for the wind, or is also going down to the downslope.
You still need some visual inspection after.
Yeah, of course. I mean, of course, the user is always the one that is saying the truth. But anyway, what I was saying, that maybe there is a snow, but it's very thin layer of snow, and so maybe it's also difficult to say sometimes. Also, the user, when you have shadowed areas, for example, it's difficult also to visualize a false color composite and say there is no or not. So also the user can be wrong. In this case, since the algorithm is very simple, it might be that it fails. So what you could also do, if you want, we can try. we can also change the threshold, for example, and see how much different is the classification mark. If you are curious, we can try. So, what do you want to insert as a number, maybe? Um, so, of course, if we increase the number, I would expect less snow, right? So, let's try it with 3.5. Let's try. Let's see what happens. Yeah, now I don't remember the previous image, but I don't think it changes so much. Yeah, maybe a little bit more snow-free areas, because if I'm not wrong, these small spots were not there before. Maybe let's try to give another name to the output to keep trace of the threshold. Yeah, so I don't see that much difference. Let's try to plot both. Yeah, maybe like this spot, it's a little bit bigger. It's my eyes, or do you agree? But very, very small differences. Yeah. Let's try maybe to put I don't know, 0.6. What happens? No, also not big difference. That's weird. I know, you see that with 0.6 now, you see that this spot is bigger. Okay, also this area is a little bit bigger. Maybe not so many difference if you focus on this small spot, because it's easier to visualize it. Yeah, this became a little bit bigger, but yeah, this makes you also aware that maybe these threshold methods are not the best, because yeah, it makes sense, but also, I mean, depending also on the illumination conditions, the threshold you should apply might change. So maybe in this case, it works with also different threshold, because the image is quite clean. But if you are facing more complex illumination conditions, we need to go to more complex algorithms. And also,
For this threshold approach, it's also always useful if you plot the result, and then usually if you have these two classes, you see really one part of the histogram shows the no snow, and the other is
yeah,
much easier than identify where it would set the.
yeah, exactly. And also, yeah, also in this case, most of the pixels, because the tricky condition is also when you have mixed pixels, snow and snow free. In this case, all the pixels are completely snow, full of snow. So, but yeah, the idea to not use a fixed threshold, but to look at the histogram is for sure a good idea. Okay, also to keep the time, let's go to the second exercise. And now we are moving to November. That is May in the northern hemisphere, and we will try with Sentinel-1 to detect snow, wet snow and dry snow, because the SAR is sensitive to the presence of liquid water inside the snow, and so there is also a state-of-the-art algorithm that is very basic from Nagler and Roth, that they apply a threshold on the backscatter to identify whether the snow is wet or dry, because when the snow gets wet, you have the backscatter that is decreasing. Now here, just also to understand which acquisition, which track, I'm using an external function that I was importing to see the list of this is using the another tool, another catalog that is the one of the Alaska Satellite Facility, that if you're using Sentinel-1 data, probably you know. And so we can visualize when the acquisition happened, and what is the track, what is the name of the acquisition, and so in order to do properly this exercise, it's better to consider, because we need to consider different scenes. So we will do a ratio between different acquisitions, but we keep the same track, because depending on the track, you have different looking angle. And so this would mix too much and add too much noise. And so basically we are selecting the same track to be sure that we are not doing, we are adding uncertainties. For this purpose, since we are using the processing of the Sentinel-1 data, that is the gamma zero, is called gamma zero. So we have a process that is called SAR backscatter, and you can ask for different level of Sentinel-1 processing. And we wanted to use this that in practice reduces the distortions of the signal by correcting for some terrain properties so the DEM basically. But this is unfortunately not available in CDSE. This process, the process, yes, but not this gamma zero. And so we switch to another backend, so we can also look at another backend. This is the openEO platform backend, so from Daniel. And now we will try to authenticate to the backend. I hope it works for everyone, because here you are asked to insert your institution. So in this case, Evrak is there. Otherwise, I don't know if you can log in through another Google, GitHub, or whatever. Google. Okay, perfect. That's perfect. So Okay, so we are now on the other backend. And yeah, this SAR backscatter, basically you are reading the data, you are removing the thermal noise, you are calibrating the data, and you are applying this terrain correction specifically for this gamma 0. Then what we also do, so you see that we have again load collection. We are loading Sentinel-1 GRD data in this case, similarly to before what we did with Sentinel-2. And we are loading the two VV and VH polarizations. And then we apply the SAR backscatter process. And also we do everything in one cell here, is to convert to a linear scale to decibels. So I just wanted to say that maybe we are also doing the exercise here, now for us the same date when we have also Sentinel-2 acquisition. This I was looking specifically for this to show you also the false color and have a reference also from the Sentinel-2. So let's run this. Okay, this was the again. See, now what we need to do is basically, so this the previous one was the date we want to classify, but we need also to define a reference period in order to compute the condition where when you have only dry snow. And this is again in July, that is full winter. So in that period, the snow, we are sure that is completely dry, and that will be our reference when we compute the difference in terms of backscatter. And of course, we take the same track that in this case, what is also nice here, you can add another filter on a property that in this case is the orbit direction. And so since we are considering here only descending tracks, we add this filter here and we automatically look only for that specific track that we want. So this worked. Now we are taking a mean over time. So this is another process that it's useful in openEO. So you apply a reduced dimension, and the reducer in this case is mean, but could be also something else like I don't know, median. There are some available reducer or max, mean. And the dimension, because you have to remember that we are working with data cubes, so with these cubes of x, y, time and bands dimension. So we apply the process along a specific dimension that in this case is time, because as you can see here in the list, we had in this time period, that is 1 month, we had two images, images for each track. So we could also select only one, but to filter a little bit the noise, we are doing an average over time. And yeah, let's do it. You can notice that here it's quite fast to run the cell because we are not really launching the job, but we are just creating our process graph. So only when you really call the download or you launch the job, then you are really connecting to the backend, and it's doing the real job. In this case, it's just the syntax, I can say. So here it's very fast. Oh, maybe I was missing a cell here. Oh, I should have run everything, but okay, now it's working. So you see that now we are computing the difference in terms of the backscatter. So the image to classify minus the reference image. In this case, since we are in decibel, is a difference, but it would be a ratio if you are working not you are not converting to decibel. And then once we have the ratio, so it's called the ratio because of this. It can be confusing. Is a difference, but in reality, is a ratio depending on the if you are using a logarithmic scale or not. But yeah, then we are applying again reduced dimension, and in this case, you see that the dimension where we apply the mean is bands. So because we have VV and VH, and we compute a mean, and we consider both polarization, and we compute a mean. Then we apply this resample spatial to filter out the noise. So if you have worked with Sentinel-1 data, you know that they are very noisy sometimes. So what can be done is to apply, in this case, the simplest, very simplest version of the speckle filter. That is simply an average over in this case, 100-meter footprint. And this is done with this other useful process that is called the resample spatial. And also here you can define the method you want. Okay, now it's time to apply the threshold in decibel to all these output that we will get. In reality, here I see there is a little bit, no, it's not a mistake because I was applying the threshold before the speckle filter. Let's apply it to the image that is also filtered after applying also the speckle. It doesn't make it so much different. The only difference, as I was saying, is that it's a little bit less noisy. And so let's go. So now you see it will take longer because it's okay. We load the collection. Maybe, but were you able to log in?
Yes.
That's, I don't know why this is just a weird error. So you see, it was better not to delete the output folder. Let's try maybe not to apply the speckle, just let's try to, if it's a little bit did someone manage to run the cell, or you also got an error? No, it's working. Okay, without the speckle, it's working, so maybe that's why I removed it in the previous version. Maybe because the error was about the memory, something like. Maybe I don't know if the medium server is not enough for. I don't know. Honestly, I don't know, but because the only difference is that I was also applying this sample spatial. Maybe let's try again for curiosity if it's working. No, it's not working. So seems like the error says the driver is used too much Java memory. So I don't know. My suspect is that maybe could be that it's too heavy the process.
If I use the speaker, it works, but it doesn't work if I download. The error, in my case, the error is when I the comment to the downloaded file.
Yeah, because if you don't download, you're not really running the process. So, so you're not, basically, you're not doing anything. You're just creating the process graph here, but you're not running your code. So that's why it works. Okay. Sorry for the error. I will investigate it better, but for the purpose of the exercise, maybe it's now it doesn't work anymore. Also with uh, okay, but we are safe because so I suspect that this is not related to something wrong in the syntax, but is something on the backend side. It's working. Maybe we are too many people doing the same at the same. I don't know, but if not, so I'm asking you since you're on the openEO platform team, so you know better than me the backend. But
Yeah, I think we need to check what exactly this error means, but I think what you said that somehow it's causing a problem.
yeah,
But it's too heavy or
one way.
but it's not that complicated, so maybe it's some noise or something.
Yeah.
Smaller something.
Maybe it's also because of we are using the Jupyter lab of the Copernicus data space ecosystem. I don't know if it can be also the issue, but yeah. Now now I need to download this data also for Sentinel-2 since I removed from the output. So sorry, I'm going back to the previous exercise and I will download this 33 November. So I just go back quickly here. If you also deleted everything, you need to do the same. And the date was November 23. I'm not wrong. Yes. So let's change also here. The study area is the same, so basically everything is the same. We just change here also the name 24/11/23, and we run again this to download also the Sentinel-2 image to have the false color for reference. Okay, now that we have also the reference, let's go back to the previous cell. Let's ignore the error because previously it worked. And we can now see. So it's the same date. On the left, you have the false color composite from Sentinel-2, and you can see that the snow now is very patchy. It started to disappear, and so as expected, we get this wet and dry snow classification. You see that especially the patchy areas that are more downhill are classified as wet, as expected, because the snow is melting and is full of water. While if you go a little bit upper in the, also this is the part that is above the glacier, so probably here the snow is much colder and is still dry, it's not melting yet. But the patterns we get, you see, are quite nice, reproduced. Of course, also this is a very basic example based on thresholding, so you don't get the most accurate output, but for a speed up analysis is a nice tool that we can use. Okay, so let's move to the last exercise. Then I would have an additional notebook to show you. So, but let's conclude this one first. So the last period is the summer period when you have both ice and snow. So the aim here is to detect whether there is ice or snow on the surface. So for doing this, we apply again. I put also the references if you are interested. So we apply again a threshold-based classification. And this is, again, we go back to optical data, so Sentinel-2. So let's switch again the backend. Now you won't be asked again to log in because we did it previously, so it saves in the memory the credential for a while. Then what we do is we do something a little bit different here. So it can be an interesting example because instead of giving the bounding box, we load a GeoJSON that is saved in this case also in the GitLab. So we load the GeoJSON, so you see that you can easily communicate and load also from a URL an external file that in this case is a shape file, a GeoJSON, but could be also, for example, if you want a model, you want to load a machine learning model, for example, that is predefined. There is also a way to do it, to import and communicate between the backend and the an external source. And why? Because we use this GeoJSON to mask the scene. So this is like the glacier outlines that are were prepared. Now I don't know if they are updated recently, but anyway, they refer to some years ago, and probably also what we will see is that the glaciers, since unfortunately they are disappearing, they will take an area that is a little bit bigger than the actual size of the glacier. So what we do is to work specifically not on the data cube and on a bounding box, but to work specifically on a shape, on an area that is only the area of the potential glaciers. And I will explain you in 1 minute why we do this. So again, we compute some indices that in this case is the NDSI and the NDVI, but also another index that is defined as the red, the ratio between the red and the SWIR band. So nothing complicated. But these indices, if you are curious and you look at the references that I put in the notebook, they are used normally for detecting ice. So okay, so once from these spectral indices, what we do, we create a candidate mask that basically represent the pixels that have a sufficient high NDSI and low NDVI, and that they might be snow or ice. So with the comment again here, download. I'm not explaining that much because these are simple algebraic operation among the indices and the bands. Then what is interesting maybe is that we have a new process that is called mask. If you want to apply a mask on your data cube, then we add dimension that I think we didn't see it before, if I'm not wrong. So this might be used sometimes when you work with also UDF that are user-defined functions. So sometimes they get you a bug if you don't have some specific dimension. So it's better maybe to add, and we can also rename the band that in this case is the ratio, and this can be useful also if you merge several data cubes. So because you can also merge several data cubes. So let's do it. So you see, you can add a dimension, you can rename it, specify the type, and yeah. In the meanwhile, it's running. So then, to separate among snow and ice, what we do is to apply to this ratio the Otsu method that is basically just a method to find the threshold based on a histogram at the end. So similarly to what also Daniel was suggesting before for the NDSI, also in this case we do this for this part. So to find the perfect threshold, we apply the Otsu method. That there is a nice function in scikit image that does this without too much effort, but the problem here is that we cannot directly import a library and apply the function because it's not an openEO process. It's a function that is from an external library. So what we can do, the workaround, is to define user-defined function where we import the library and we can then apply this function. So so a UDF is needed when you need to do something that you cannot do with the basic process. You can also list all the processes that are currently available in openEO. So if you want to do something a little bit more fancy, you need to define your user-defined function. So you see here the syntax, and basically it's simply applying this function from scikit image. So what I want also maybe to highlight here is that I was mentioning before that we are importing a GeoJSON. So the standard way to apply a UDF is to use apply or apply data cube. But in that case, you are working on chunks because the data cubes are divided in chunks on the backend side. And so sometimes this is not convenient. Depends what you want to do. If you don't have a spatial influence in what you want to do, So, for example, in this case, dividing the glaciers in chunks that don't have a spatial coherent pattern, so would result that for each chunk you get a different threshold, but it's not said that a single chunk contains a single glacier. So what is more convenient is to extract a single threshold for all the glacier to use apply polygon. So we are extracting the threshold over all the polygon that is defined by our GeoJSON. And this was the best way to do it. So I hope it's more or less clear. I don't know if you have questions. I Are you following more or less? I'm also not on the backend side, so maybe I cannot really explain so well what is happening on the backend side because I'm more a user. But if you have questions, please ask. So you can see here that our UDF worked. You can see that the process graph has become a little bit more difficult, bigger, and yeah. Yeah, now we can visualize the results. So you can see that we have again the false color composite. And you can distinguish because the ice is a little bit darker. So you can see also, if you are not really expert, that these darker areas are the ice, while the more bluish cyan areas are the snow. And this is the result of the classification that I would say it's quite well representative. So again, a simple method that worked well. But just a curiosity also for you that maybe you don't know the area in this specific Azufre glacier. So you see that correctly, the algorithm classified as neither ice nor snow, this, this part, this area. And you see that it's white in the false color composite. So guess what this is? Do you have an idea what could be?
Because of the name for Spanish people, it's easier, I guess. It's sulfur. No? Okay.
It's sulfur.
Sulfur?
Yeah, because there is a volcano actually there, and this is the smoke of the volcano. So
I think it's sulfur.
yeah, see, I also didn't know because I don't speak Spanish, so good to know. And yeah, could be also how to say a cloud because it's similar. I also guess the reflectance is very similar, smoke and clouds, but. Because in this example, we didn't apply any cloud mask because on purpose I was choosing cloud-free or almost cloud-free scenes. Of course, there is also a way to apply a cloud mask in openEO. Also now we are working to because we can use the SCL band, for example, of level 2A data to apply a simple cloud mask. Now we are working with Vito, the colleagues of Vito, also to improve the cloud retrieval and have something more specific also that works in OpenEO because the quality layer of Sentinel-2 is sometimes, especially for snow applications, because it also depends on the application. Since snow and clouds have a similar spectral signature, for us it's very tricky to retrieve and distinguish among snow and clouds. So now this first notebook is over. I hope you managed to follow it and it was interesting. I have a second not so don't escape because I have a second notebook that is shorter, by the way, and I think it's interesting to see it because it's another application of a UDF, and so. I will explain better the issue that I was mentioning about the chunks. That of course depends always what you want to do, but for some algorithm, the spatial chunking can be really messy, and you need to change all the architecture of the algorithm. So you can open the notebook called Hillshade. And yeah, in this, it's much simpler also because we have only 20 minutes left. So in this exercise, we just replicated the GDAL function for getting the hillshade inside a UDF. So let's start again. Let's import the libraries. Let's define the study area that now we move to South Tyrol, since I'm from South Tyrol, and this is called the Fleres, is nearby Sterzing, Vipiteno. Maybe you know the yogurt, and so let's move back to the Alps. Of course, if you are curious, you can also define your own study area and try later the notebook at home. And yes, let's authenticate again. Now we load the DM. In this case, in CDSE, there is the Copernicus DM available. So as a normal collection, we load the Copernicus at 30 meters. And let's wait. Yeah, because as far as I know, it's missing some similar function in openEO as GDAL that returns you slope, aspect, hillshade, or whatever topographical feature. So you have either to construct it through processes, but as we saw before, the processes are more like algebraic operation, reduce bands, mean, average, these kind of things. But if you are going to more complex stuff, the only way is to define UDF. So this is the DM. This is our basin. So this is, I reported here the UDF for the hillshade. I modified it in Italy GDAL, but I was looking at the GDAL source code, so it's using really it's following the Horn formula for slope and aspect. So what I would maybe let you know, mention here is two things. One is that for a UDF, you need to give a data cube as input, and it returns a data cube of the same dimensions. So this means that it's not possible. I don't know if it's planned for the future, but it's not possible to give a data cube and extract a shape or a single point. You have to think to keep always the same dimensions. And another thing is that you can also, that it can be useful, so was one of my first questions when I started working with the UDFs, is that you can also give the context. So if you want to set some user-defined parameters as input, so as normally you do with Python functions, and this you can do in this way because it was not really user friendly how to do it. So you need to give here this add this line when you define the UDF, and then you can in this way also add some user defined parameters as a dictionary that is called context. So let's try to do the job this exercise by using apply dimension. So this what happened? Ah, I didn't run the previous cell. Sorry. So let's try to do by dividing in chunks, as I was mentioning. So by using apply dimension, you are reproducing the function over dimension that in this case, yeah, can be a little bit confusing because it's a DM, so we don't have the time dimension. But let's imagine we want to do the same for a data cube that also has the time dimension. So you define the dimension where you want to apply the same function that is can be time bands or a spatial dimension. And what you will get is that you see this is the effect of the chunking. Also because when you run also the GDAL function, you know that you can set compute borders true or false. So in this case, since the border are not computed, you really see the effect of the chunking because you have a stripe of I don't know 2-3 pixels that is no data. And for this case, okay, was not a big problem, I would say. But if you really need to give to your function all the area as input to the computation you are doing, then it can become a little bit tricky because sometimes, as in the case of the Otsu threshold, we need to give all the area to compute that specific threshold. And so this chunking can be a little bit tricky sometimes. So it's something that you need to keep in mind. How we can avoid this in this simple example is just to instead of using apply dimension is to use apply neighborhood. So we compute, we define, normally these chunks are 256 pixels, sometimes 256 if I'm not wrong. Maybe it depends also on the backend, I don't know if it's fixed. But here we can define our chunk size. So we can, as a user, we can define. And we can also define an overlap in order to avoid the border effects. So you see, we can run again, and let's check that we are getting. Yes, tell me.
Sorry, one question.
Y-
May apply neighborhoods and use apply kernel.
Apply kernel. Well, I think I've never used apply kernel. I think it's more or less the same. I'm not sure about. Maybe we can quickly check in the meanwhile that is running because I'm not really familiar with apply kernel. So I can also show you that you can find all the because yeah, apply a spatial convolution with a, so you need to define a kernel. It's a little bit more complex probably for in this case for the task that we are doing. Apply neighborhood is enough because here you also yeah. Yeah, you see, they also say for cases requiring more generic focal operation. Yeah, so yeah, yeah. Yeah, in this case, since we didn't need a specific, nothing specific, apply neighborhood was enough. then it's still, I mean, sometimes also the documentation is not so so clear, and so you need to put your hands dry and see what it works. And you see that here now the hill shade is complete, is without changing effect. And yeah, I just wanted to propose maybe as a last exercise to change the context, so to change the because basically you are giving the altitude and the azimuth of the sun. So based on the position of the sun, you get different shadows and hill shade. So I don't know if you want, you're curious to change it, we can do it. You can tell me, give me some numbers. So 45 means that so this is the azimuth. So is the altitude. 45 means that is more or less in this position. So we can put 90 maybe to see when the sun is completely up, noon, yeah. And the azimuth, I don't know, let's put a random number. Let's put, I don't know, 60, whatever. Yeah, of course, for us, we want this to be given dynamically, because as I was mentioning before, this is part of the algorithm that is done for the machine learning training. So we also give the yield shade as a parameter. So we look at the time of the acquisition of Sentinel-2 image to get the proper hill shade. So it's one of the features that we use for the training of the algorithm. And so, of course, we cannot work with a fixed altitude and azimuth, but it's necessary to give it as a context.
Make the question, but the altitude angle measures depending the sun, depending on the time of the day, and the azimuth depending on the season. Right?
Yeah. And yeah, now I don't think maybe it's always difficult to see the differences, but also because with we need the mobility in QGIS maybe to see better. I don't see that much differences, but I guess they also, because maybe 45, 90 is not but still you should see a difference. Weird.
Well, we're getting to understand how it works.
Yeah.
The results might be not that relevant, but
Yeah. No, but just also for it's always nice to interpret. But yeah. Yeah, I don't know if there are some questions or some comments or so suggestion from experts of the backend. No.
This-
I do.
somehow related also to what we were discussing the talk this morning about the open API, openEO API, etc. Right? So I guess that with for the conversation we've been having with Tom yesterday about where to put the data, and so the CDSE, etc. Would the openEO, for instance, would be able to have all the information that we are planning to have for the Open Earth platform, for instance, besides the data, to have also textual information, maybe media and stuff like that, or that should come from other places?
I would say it should come from other places, because how the openEO is integrated in the CDSE is really that it takes the data that's there, so that's where we could bring our data, but then it's just a processing backend, so it just defines what you want to do with that data.
Okay.
And everything else like contextual or how you use it then or displayed in the notebook, that's then up to you as a user, but there's not a way of yeah.
Okay, so I wanted to understand those
Yeah.
or abilities so that we can keep on.
Yeah. No, I agree also because I think now we already met also a very complex algorithm over large areas. So from my experience, so also what we were thinking for the other project that we are planning to work on the Andes is maybe to have some use cases, also some simplified versions where the user can have quick results and get like with a click first estimation. But yeah, anyway, also for the monitor, we were processing everything locally. We are not migrating completely to OpenEO.
I think what is cool and would be cool to also continue doing when we use OpenGeoHub to process something that we then also publish or have these algorithms within the on CDSE it's called EO Plaza, so that other people that want to do similar things, they can go there, they see the algorithms and can use that as starting point for their research, so that we have some of these common Wikipedia paper to see, okay, how did other people that have similar technical questions, yeah, do their work.
Understood. Thank you.
No, I think also that if the user community is growing and there's also because we were really in touch with Vito also to say the bugs, the problems that are also on the backend side that of course for users is a little bit difficult to interpret sometimes and we don't know what is really happening but if the community will grow probably also it will become more easy to use so I hope that something that will continue in the
Yeah. I mean, more people use it and provide feedback or share requests of what's missing, the more likely it is that it says, yeah, there's really need and demand. And it's always much easier to develop a functionality when you have a concrete use case and someone that gets value out of it than just, yeah, knowing from our side what's missing.
I guess you were very clear in your explanations. That's at all.
Okay, nice. Either I was too clear or I was not clear at all. That's yeah. You never know where you're lying, which side of. No. But anyway, if you the notebooks are public, so if you want also to take inspiration in the future from it, and if you have questions, you can also contact me. It's always nice to talk about common problems. Okay, so thanks for attending. Thanks.